Good morning or good afternoon. My name is Atarot Azizi Namini with Florida International University and Director of the IBT/ABC-UTC. Very warm welcome to more than 700 people that have signed in to listen to our August 2024 monthly webinar live. We are delighted to have with us today Michael Knott, who is a Senior Vice President Emeritus with Moffitt & Nichol, and Mike Winters with North Carolina Ports Director and Moffitt & Nichol, to give us a talk on general overview of the vessel collision risk analysis, which is a very hot topic, and we are sure that many of you are very interested in this topic nowadays. During the registration process, we also received a number of the questions that we are going to try to answer it as time permitted. If the time does not allow to answer all the questions, we are going to get the answer to them and then post it on our website. But if you have some additional questions, please post it on the dashboard. Very important announcement. Please take advantage of early bird rate registration. Registration for the upcoming 2024 World Bridge Engineering Conference is right around the corner. It's going to end August 23, so please take advantage of that. There's a link that you can register. You can go to our website to conference page, and there is an online registration and all kind of information for you. Conference is shaping up to be a really good one. 32 states DOT have co-sponsored, in addition to the Federal Highway Administration. We have lined up great line of keynote speakers, speakers from South Korea, from the Europe, is going to be there to give you an overview of what all goes on, not only in the US, but also overseas, as far as the innovations in the bridge engineering and the ABC. We have speakers from the Federal Highway Administration, from the contractors, and also US Army Corps. The conference program is set. If you go to our website, you can click on a link that we have provided, and you can see the list of all the presentations that are going to be made. The conference is 3 days: Wednesday, Thursday, Friday. Wednesday is all just a keynote talk. We are going to be in the same room. On Thursday and Friday, we are going to split. There's going to be 5 parallel sessions. There will be 140 half-an-hour long technical presentation on Thursday and Friday. There will be a free workshop. December is a very busy time in Miami, Florida, as you might expect. Therefore, we have a block of room, but they are going fast. Please reserve your hotel room at a special conference rate. There is we still have space for exhibitors. So far, I think we have more than 35 exhibitors that have signed in. There are some additional 20 or so space available. If you like to exhibit, please go to our website. There is the information on how to reserve your exhibit booth. If you are employed by the county, by the state, you work for the state DOTs, there are travel scholarship that's available, and we have a link in there, and we are going to finalize, we're going to announce that who is getting the travel scholarship by August 23rd. On a Wednesday evening, there will be a reception. On Thursday evening, don't miss this, there will be a workshop on shotcrete with ultra-high performance concrete. I will be giving basically the workshop. This is we are going to provide you with all the details. This is a paradigm shift for repair and the strengthening of the existing bridges. So again, all the information is there. So please go to our website and get all the information. And again, early registration ends August 23. So at this point, I'm going to turn it to Kathy to share with you some additional news related to the bridge engineering. Kathy?
Thank you, Atorad, and thank you all for joining us for today's monthly webinar. Before we get started with the webinar, I'd like to share with you some of the upcoming events, both from some of our partner organizations and our own. First, the American Composites Manufacturing Association, the ACMA, will be hosting the Composites and Advanced Materials Expo, CAMEX, which is from September 9th through the 12th in San Diego, California. More information and registration can be found at the links shown on the screen. Next, the Precast Pre-Stressed Concrete Institute, PCI, will be having their PCI Committee Days, September 23rd through 27th in Nashville, Tennessee. This is a kind of an earlier announcement, but the big event for PCI every year is their national convention that's held in conjunction with the Precast Show. And they've recently published information on that. So we're just giving you an early show that February 3rd through the 7th in Indianapolis, PCI will be having their main event. The next one is the AASHTO, the American Segmental Bridge Institute. Their 36th annual convention and committee meetings will be held October 20th through the 23rd in Atlanta, Georgia. More information can be found at the links. And now some information for the IBT, ABC, UTC. Once a year, we have in-depth web training, and it's very similar to the webinar series that you're attending today, but this is longer. So we get 4 hours to really delve into a subject. So this year, the in-depth web training is on September 10th, so less than a month away. It's from 11 to 3:15 Eastern. Our topic for the year is innovations in ultra-high performance concrete. And you can see from the list on the screen, it's really the preeminent scholars, the preeminent people involved in the ultra-high performance concrete industry. So please join us for that. A little bit more information on the in-depth web training. On the screen, you can see the agenda for the day. This can also be found on our website. So please do go to the IBT, ABC, UTC website and look up more information on the in-depth web training. The registration is open, so please do get registered as soon as possible. And you will be seeing some additional announcements come out on this, but it'll be a really, really great training session, so please join us. And now our next monthly webinar will be what is artificial intelligence and machine learning. Our presenter for this will be Mark Finlayson, who's also with the Florida International University. It's a really interesting, very topic that's in the news very much. Mark does a great job of really talking through the definitions and things to think about as artificial intelligence and machine learning enter our daily lives. And now we'll get to today's webinar. So today's webinar is a general overview of vessel collision and risk analysis. We're joined by Michael Knott and Mike Winters, both with Moffitt and Nichols. There will be a question and answer session that follows today's presentation. Please feel free to add questions in the question box that is in the dashboard on your screen. And now we'll turn the presentation over to Mike.
Thank you very much, Mike Winters, and I appreciate the opportunity to speak to this group. So today we're going to give a basic overview of the AASHTO vessel collision risk analysis, but we're also going to spend some time talking about pier protection systems and the types of protection systems that might be appropriate. So we're going to basically look at some background of vessel collision, get a little bit into risk analysis, but not too deep, just to give you an overview. Talk about some pier protection systems, and then we have some final thoughts. Now, this presentation has almost 40 slides in it, and we're not going to cover the content on every slide in detail. So afterwards, you can download a PDF of this presentation and look up some things that we just won't have time to get into, but we do want to hit a few highlights. So The recent collapse of the Key Bridge in Baltimore certainly has brought a lot of industry and public focus on bridge safety. And there are a variety of accident investigations and litigation underway. So accidents do happen. It's only a matter of time. I often say, if you build it, it will be hit. You put an object in the water, be it a pier, a bridge pier, or a terminal port facility, or a pole, at some point in the lifetime of that structure, due to whatever circumstances, it's probably going to be hit. Bridge collapses have obvious consequences. People die. Oil spills occur. Political turmoil where people lose their jobs and governments can be turned around. Obviously, major transportation disruptions and large economic losses. The largest of these losses are usually the motorist inconvenience costs, where motorists have to take a detour for the years it takes to replace a bridge. And if you detour 50, 100,000 cars a day, that adds up. Of the collapses that have occurred since the early 1960s, about half of them are in the US. Just to note that on average, we have about 5 collisions per week, which are of a minor nature. They do some damage, but not significant and not leading to collapse. Next. Well, why do vessels get in trouble? Well, there's a variety of reasons. Most of them, the highest reason is human or pilot error, depending upon which statistics you follow, 60 to 85%. And the things I list on this slide are not exhaustive. There are a bunch of factors that can be put in here. But one of them is most international vessels have international crews, and not all of them speak excellent English. And sometimes there can be misunderstandings between a local pilot telling a command that's not quite understood. There can be mechanical failure. This is obviously something that happened on the Key Bridge. In most circumstances, tend to have some kind of an adverse environmental component to it. Heavy fog, rainstorm, strong winds, that type of thing. Next. Well, these collapses occur everywhere, inland waterways and coastal waterways. And though we're talking maybe more with the focus on ships, obviously, we have many more bridges in our coastal waterway system that are subject to barge impact. And we've had a number of bridges collapse due to barge collision. In the lower left of this slide is a railroad bridge where a barge hit it. A train was passing a few moments later and went into the river near Mobile, Alabama, and a number of people were killed on the railroad. Next slide. So 1980 was a turning point in the development of standards for ship collision or barge collision. So in that same year, there were 2 major collapses. The Sunshine Skyway Bridge collapsed in Tampa Bay. Empty ballasted bulk carrier was caught in a severe thunderstorm and was blown off course. And in the picture you see in the upper right of the Skyway Bridge, the ship did not hit the main pier near the channel. The ship hit the anchor pier about 800 feet away from the channel. And it's important to note that twice as many bridges collapse due to vessels hitting approach piers than they do main piers. So it's not just the main piers we're concerned about, it's the number of piers in a central area near the channel. In Sweden, the Tjorn Bridge collapsed when an empty vessel was just ever so slightly off course. In the lower right, this was a very graceful arch bridge that won several international awards for aesthetics, but the ship was slightly off course and the deck house of the ship caught the arch and the bridge collapsed. So prior to the 80s, basically, the older codes considered these types of things, these extreme events, as acts of God. So in 1988, there was a pool fund research project sponsored by 11 states and the Federal Highway Administration. I had the great privilege of being the principal investigator of that study. It included consultants from Denmark, Ole Damgaard Larsen from CUI Consult. We had Professor Gerhard Weissen, a noted naval architect in Germany, specialized in ship collision, and we had Dr. Fuji from Japan. and some of the risk analysis work he was doing there. The result of this research project was in 1991, the adoption of the AASHTO Bridge Guide Specification for Vessel Collision. That code was used for 18 years, and then in 2009, a second edition was issued with some minor revisions and updates. The guide specification has since been superseded by the AASHTO Bridge Design Specifications, what I'll call the code itself. Now, the guide specification had over 240 pages of vessel collision analysis and design information and background and worked examples, and that all was condensed into 20 pages in the code. And so if you just read the code, you will have what I think of as a limited understanding of vessel collision. So this second edition is really a critical reference when using and understanding the code provisions. AASHTO had moved it into their archives section, but have recently brought it back out. It is available now in AASHTO publications. It's not in their catalog, but if you go to AASHTO publications online and search vessel collision, you can purchase the second edition of the guide specification. Next. So a quick overview. This was the first time risk analysis was used to determine the design condition for bridges. And so we use the procedure to estimate the probability of bridge collapse, and we compare that to a standard, and then we do something to bring the bridge in compliance with that standard. Part of the vessel collision risk analysis is we select a design vessel associated with each pier in the waterway. It could be a different design vessel as the piers are further away and in shallower water. There could be a different design vessel inbound than outbound. That's sometimes the case for river situations. For critical bridges, the risk of collapse is 1 in 10,000. For non-critical bridges, it's 1 in 1,000. This does not mean we expect bridges to last 10,000 years or 1,000 years, but just that the risk of vessel collision and collapse of that bridge within its lifetime is vanishingly small. The code has some simplified examples of the principles of how to do vessel collision, but these simplified situations are rarely real world. In the real world, we have curved navigation channels and side channels and other geometries. And so these basic principles need to be adapted for the local circumstance. Next. Flow chart here, I won't get into the details, but basically we have 3 major areas of data to be collected. There's waterway information, the channel geometry, water depths, water currents, history of previous accidents. There's information about the fleet to be collected, the vessel types and sizes, their loading conditions, particularly the ballasted thing we'll talk about in a moment, transit speeds and the paths the vessels are moving in the waterway. And we also need to determine the number of times a year the vessels are passing under the bridge. We collect information on the bridge and the site characteristics. If it's an existing bridge, obviously we have the plans. If it's a new bridge, we get to decide where the piers go. So span lengths, pier geometry, ultimate impact resistance is a critical component of the analysis. Obviously, geotechnical data is important. Vessel collision is combined with scour, so understanding scour and the scour information is vital. We do the risk analysis, and out of this comes a probability of collapse in our design vessels. The guide specification had 3 methods, 1, 2, and 3, we called them for simplicity. Method 1 was a semi-deterministic procedure for inland waterways with barges that's somewhat simple to use, and you get your design vessel. Method 2 is a full-blown risk analysis, which is really applicable to waterways with a wide variety of either ships and barges of different sizes. And then method 3 was a cost-benefit analysis, where we take the results of the risk analysis, combine them with cost to determine what's the most effective way, cost-effective way to spend money to protect the bridge. If it doesn't meet our criteria, then we have to change something, change the bridge, do something to bring it in compliance. Next. The basic equation in the code is shown here. Again, I won't go into all the details, but the annual frequency of collapse consists of several components. N represents the number of vessels organized by type and size and loading condition, which can strike a bridge pier depending upon water depth. There's a probability of aberrancy, which is how often does the vessel go off course. This includes a accident base rate based on historical information. There's a geometric probability that says, well, if the vessel goes off course, it's aberrant. Where is it? This geometric probability is not the distribution of vessels that are in the channel. We'll talk about AIS here in a moment, which gives us information of the thousands of vessels that are transiting the channel. And one can do all kinds of statistical work on that information, but that gives you the vessels that are in the channel. This geometric probability is the rogue vessel, the 1 in 50,000 transit vessel that's off course, and we're asking the question, where is it? And that's what this geometric probability attempts to do. We do a probability of collapse, so if the bridge is hit, will it collapse? Sometimes it's a minor collision, it won't. Sometimes it's a big collision, it will. There's a protection factor. Are there things upstream, downstream, or protection structures to protect the bridge? We have to make estimates of what that is. And then there's a growth factor. Are more or less vessels expected to transit this channel in the future? We typically take the analysis to the midlife of the bridge in question. To highlight one last thing before I pass it on to Mike Winters, every one of these factors has engineering judgment decisions. And this raises a basis of design concern for state DOTs and FHWA for major bridge design build projects. If competing firms are allowed their own creative analysis, there is the potential to game the code, where rather than making reasonable decisions about these factors, one can make decisions that maybe others would consider unreasonable. And a series of minimum unreasonable decisions could result in a bridge structure that doesn't meet the intent of the code, which is to stop or redirect a ship from hitting a bridge and making it collapse. Mike Winters is now going to continue the talk with some highlights and other thoughts. Mike.
Thank you, Mike. And I did want to take just a few moments to acknowledge Mike Knott. It has certainly been a pleasure and an honor to be able to work with Mike Knott for the better part of 25 years. It's been wonderful for me to be able to glean the knowledge that he has. As Mike mentioned previously, he was the principal author of the AASHTO Vessel Collision Guide Specifications. So through the course of my careers, I've come across some of these complex issues that Mike had mentioned previously. It's been certainly easier for me to bounce ideas off of and coordinate with him on the correct path forward on how to address, once again, these complex issues. Did want to also just kind of expand on just for a second. Like Mike mentioned, there is a lot of information in the Vessel Collision Guide spec. It was pared down from over 200 pages to about 20 pages in the code. But even in the 200-page vessel collision, there were examples, and as we know with codes, they're usually very simplistic. I harken back to our days in college whenever we had examples in textbooks. They were usually very simplistic examples. They gave the basics of how things were done, but then we needed to take that information and proceed that through to the real world problems, which are usually a lot more complex. So the vessel collision risk analysis portion, it is a complex, it's a very complex computation, and that's done. There's a lot of nuances that go into it, and as well as when you back in on the protection structures, there's a lot of issues to address there as well. We only have time, unfortunately, to touch on this. I do want to point out that at the upcoming conference in December, that Mike Knott is a keynote speaker. He'll be providing some additional information. I am also presenting a paper at that conference, providing hopefully some additional information and with regards to this subject matter. And so, but with the knowledge that Mike Knott used to actually present a 2-day FHWA course just on vessel collision, the risk analysis portion, we could probably do weeks and weeks trying to go through all the complicating aspects of it. But you know, once again, we're just trying to highlight some of the things here in this program today. For the annual frequency of collapse computations, they are relatively straightforward as far as the code equations go. We typically utilize an Excel or MathCAD type sheet to automate the process. It is very site specific and it is a very repetitive process. I do caution though that the reuse and the modification of previous risk analysis, it can be problematic. I've spent early parts of my career trying to develop the super spreadsheet that could do it all. Unfortunately, every time I've come across a new project, there's usually a small nuance that kicks everything back. So typically the way I've done it is I've actually paired I've taken this massive spreadsheet, which for some projects could be hundreds of tabs and thousands of pages long. I've paired it back to the inputs and kind of rebuilt them from scratch. Concern is that you start on something and you're in something so voluminous that it's hard to find where there may be an error in the calculations. So starting from scratch has been somewhat of the way that I would do it. If we look over what we do is we look at the upbound, downbound vessels. We look at all the information that Mike had mentioned previously with regards to the probabilities. And what we do is we sum all of the piers, the components, and that gives us that annual frequency of collapse of 1 in 10,000 or 1 in 1,000, depending on the critical or regular nature of the bridge. We also look at the pier components, and for bridges where superstructure collision is a problem as well, then we have to account for that into the annual frequency of collapse as well. The superstructure components can be very tricky because a lot of times those are associated with truss bridges, which have varying geometry at almost, you know, a foot next to one location is a totally different geometric probability. So there is a lot of computation that goes into doing that with the superstructures, but we do account for both the piers and the superstructures. Once we've developed our spreadsheets and we have come up with the annual frequencies of collapse, once we develop the risk analysis, the program can be used to do several things. If the ultimate resistance strength of the piers has been computed, like for an existing bridge, we can solve for the annual frequency of collapse and then determine if it meets the risk acceptance criteria. If it doesn't, then we can look at doing protection structures to help make it into the risk criteria. For new bridges, we can back solve the ultimate pier strength needed for each pier. And with that, we would need to establish some kind of distribution. As Mike mentioned, rarely is it just the two piers on either side of the channel that we're looking at. We're looking at a certain zone on either side of the channel. And so we have to establish by setting up the risks to each one of those structures that could be affected by the vessel collision. The benefit of setting things up this way is that it allows us to do a lot of what-if scenarios, look at different pier locations, span lengths for new bridges, what types of pier protection alternatives might work. Mike had mentioned about the vessel gathering information. There are different types of vessels. We have the container ships, which you can see have quite a distinct overhang that has to be considered. Tankers, you can see that tanker has right down at the water line, has a very established bulbous bow at the bottom that would need to be considered. We have barge tows. Barge tows, this one's showing here is a 3 wide by 5 long. Some barges on the inland riverways along the Mississippi River in particular are incredibly long. You could have upwards of 20 plus barges in a barge tow. So we have to consider those. Cruise ships, especially, you can see in this is a cruise ship passing underneath a bridge in Vancouver, British Columbia. You can see there's a lot going on up top with regards to mast and things above the primary deck surfaces. Bulk carriers, and then articulated tug barges, which these are primarily nothing more than, they're typically ocean-going type barges that have a tug that's seated into it, creating a ship type structure. So the tug is the power plant for the barge. When we're looking at the fleet characteristics, there are several things that we have to consider. Is it ships and barges, inbound or outbound transit? And that's important because sometimes a vessel will come inbound or outbound in one of the directions loaded and the other direction light or ballasted. So what that means is a lot of times container ships will actually, they come in loaded, they'll go to a port facility, they'll offload, but then they'll take on, so they're going in loaded and out loaded. Whereas when you have product vessels such as tankers or bulk carriers, they're usually coming into a facility loaded, offloading product, and then leaving empty or ballasted. Now, most ships aren't empty. Barges can be empty, but ships, we call it a ballasted situation. And the reason for that is if you empty the ship, then it becomes, maneuverability becomes an issue. So they flood tanks with water to seed it down at least a little bit into the water to help maneuverability. And then we obviously look at the transit speeds and pass. But of important note here, you'll see this upper figure is a loaded vessel. So it's seeding in the water with a certain draft. Let's say it's 40 feet for a typical vessel. At the bottom shows the loaded and shows the ballasted condition, where you can see the draft at the stern maybe half, on the order of half of the loaded draft, whereas the draft at the bow may be a quarter of it. So that 40-foot loaded draft may only be carrying 20 feet on the stern and 10 feet on the bow. So that affects the water depths that the ship can travel in. And so that obviously affects the risk analysis. So that's why looking at the loading conditions is of utmost importance. Here, the photo here is a bulk carrier in a ballasted condition. So we can see the bulbous bow sticking out. And there's actually, I've actually seen photos of vessels where the bow of the ship's actually riding out of the water. It's in such a slope keel condition. One of the publications that we use for gathering some of the vessel information is the PANC Working Group 235. This was a recent report that was put out. Prior to that, it was a lot of Google searches trying to find vessel information. And prior to the internet, it was a lot of digging through text and other hard copy type material. But this provides a lot better information than in prior years in developing some of the ship characteristics. When we look at the risk analysis, the vessel categories, we typically break them down into DWT. And DWT is essentially the deadweight tonnage. And deadweight tonnage is not the weight of the vessel, it's actually the cargo weight that a ship can carry. The weight of the vessel, or the displacement weight, is we call it the displacement tonnage. So they are different, and wanted to note that. We'll typically gather the ship information, then we'll break it down into 5,000 to 10,000 DWT increments, trying to classify different vessel passages accordingly in those ranges. And then barges are based on either a single tow or a single barge transit. Mike mentioned previously the AIS vessel tracking. AIS is automatic identification system data. All large commercial vessels are required to have this. It is it's a downloadable information. It does require some specialized post-processing software to work with. But what you're looking at here is this is the harbor in Vancouver, British Columbia. We were looking for this project actually at two bridges: the Lionsgate Bridge, which is a suspension bridge at the mouth of the entrance of the harbor, and then the Ironworkers Memorial Bridge, which was an old steel truss bridge that was in mid-harbor. But what this information shows is where the vessels are going, where they're tracking through. You can see in the top and the bottom which port facilities they're heading to, what speeds they're traveling at, what condition they're traveling loaded or ballasted. So this provides us with a lot of information on how to gather the vessel fleet for the risk analysis. Also, going into the annual number of vessel trips, the things that we have to account for. We have to account, Mike mentioned earlier about the equations that go into the annual frequency of collapse. One of those is the growth factor. It accounts for either an increase or a decrease in the annual number of vessel trips. And typically we'll transition this to the midlife of the bridge structure. You can see over here, this is one that was done for Baltimore Harbor. It's a historical tonnage data, and what it shows us is that over the course of many years, is the tonnage traffic on the river, is it growing, is it decreasing? We established a slight increase, and once again, this is one of those things that Mike had mentioned about gaming the code. There's not a requirement that we do a growth factor to the midspan, so this is certainly something that should be considered. Sometimes there is a decrease. I have seen decreases in the amount of tonnage, but consideration should be given in that case whether or not there are facilities that have been offline for a period of time that may come back online. So there's lots of things to consider as part of the analysis. Some of the other things when we're looking at the number of vessel trips is the available water depth. If a vessel is, is 40 feet of draft and you've only got 30 feet of water depth at your pier, then can the vessel actually get there? And it's not as simple as just looking at 40 versus 30. The things you have to consider is, can the vessel actually plow through the material on the bottom? A lot of the river bottoms and coastal waterway bottoms, they have very soft mud, and these vessels transiting at certain speeds have the ability to plow through them. Back in the old days, Mike and I would just make assumptions on how far they would be able to plow through. But now with the advent of finite element analyses, what we've been able to do is we've actually done FEM models to see, and that's what's shown here in the bottom right, to see if the vessel, how far can it plow before it comes to rest. The other thing to consider is if it's a hard bottom, can the vessel actually ride up on top of? Some of the other factors that are considered in the risk analysis, the annual frequency collapse, is the geometric probability and the probability of aberrancy. This is, once again, Mike said that the code shows you what to do on very simplistic models of a bridge crossing a riverway at a 90 degrees almost. This is obviously not a 90-degree crossing. So the way we do this is we look at the vessel transit path. We've got the inbound and the outbound, but on the inbound side, there was a severe curve. So what we did there was we broke the curve up into legs or tangent sections. And then we applied an individual risk to each one of these. And what you're looking at here, the standard deviation here, is for each leg, this is the geometric probability for each one of these legs. One thing to note that in the code there, for the probability of aberrancy, Mike mentioned there is an aberrancy base rate. Just know that the base rate that's in the code is singular direction, which means that base rate is for the inbound and that same base rate is for the outbound. It would be incorrect to take that base rate and divide it by 2 with half for inbound and half for outbound. The probability of aberrancy, it goes back quite a ways. The code was originally written in 1991, which that means that the data that went into developing that code probably is from the 70s and 80s. But the aberrancy base rate that's utilized in the probability of aberrancy, it was based on one pilot on board, no other navigation restrictions, and no tug assistance. So certainly with the advent of today's modern technology, adjustments to the base rate and modification factors to decrease the base rate can be developed to account for the types of vessels and specific navigation channel requirements and restrictions, such as multiple pilots, tug assistance, and if tug assistance, multiple tugs, daytime travel restrictions, visibility restrictions, current restrictions, speed restrictions, among others. One of the major components to both the impact loads and energies is the impact speed. The way we do that is that we look at actually the vessel transit path. In this example, which is directly from the code, this is two-way traffic. So we're not considering the centerline of channel. We actually have to consider the centerline of vessel transit path. And what we start out with is the VT, which that's the transit speed in the channel that we've calculated. Once we get to the edge of the channel, then there's a linear reduction in the speed all the way out to 3 times the length of the vessel. So XL is 3 times L over A. And then once it gets to that point in time, then we assume that the vessel is basically just coasting in the water. So it's the speed of the waterway on which the vessel is traveling. So obviously each one of these curves is different for each vessel because they all have differing LOAs. So it's a different curve that needs to be included into the analysis. The ideal situation for the looking at this chart, the graph, and then knowing how the speed impacts both the force and the energy, is that the ideal situation is at a long span over a narrow channel, because what it does is it pushes your piers out both into shallower water, but it also reduces the speed. The problem situation is when you have a small span over a wide channel. So you have piers located relatively close to the edge of the channel because the speed hasn't reduced at that point in time. The AASHTO impact load. So now we've run our analysis, and from there, we're able to determine what the impact force and impact energy are. It's important to note here that you must consider both the force and the energy, not just a force applied to a bridge pier. I equate this to if you've designed a beam and the beam works for the moment capacity and the shear capacity, but then it deflects too much, then you really haven't accounted for all the code requirements. And so it's more than just determining a force, applying a force to the bridge. You have to make sure that the energy has been absorbed as well, because the ship is only stopped when the impact energy has been absorbed. And that's either by the ship, the bridge, or the hydrodynamic mass of water. And the energy is absorbed by moving that force through some distance. If the bridge pier is a rigid vertical wall, then the energy is absorbed almost primarily by the vessel. There's crushing of the vessel. But if the vessel bow is only partially crushed and all the energy is not absorbed, then can the bridge pier move substantially without collapsing? So can it handle that load and the distance required to dissipate that energy? For example, just an order of magnitude for 100,000 DWT ship impacting at 10 knots, which is not unreasonable on some of the coastal ports and bridges. The equivalent static force would be about 43,000 kips, and the impact energy is over 1 million kip feet. The bow crushing distance per the code, based on that same ship hitting a rigid wall, would be about 40 feet. So the bow of the vessel would crush 40 feet. The location of impact forces is critical. We have to consider that the bridge design for both the vessel collision must consider the barge bow, the flare overhang up top, and then also anything protruding below. The barge can hang over a column footing and possibly contact a column. Looking down in the lower left here, this is a container ship. It's actually in a lock, but you can see this dramatic overhang of the bow, where that portion might hit before the bow actually would hit. The middle picture shows a cruise ship where the nose, the bow of it, could impact a column well before the bulbous bow portion of it would impact the pier below. And then we have the Francis Scott Key Bridge collapse shown here, where it appears that that bow overhang was had clipped the column and taken it down. This is what happened at the Sunshine Skyway Bridge in Tampa, Florida in 1980. This is the bow overhang actually did clip the column and took out that approach span. Location of impact forces, continuing. The vessel collision must consider the bow shape, as we've talked about, the overhang above the waterline contacting the column, the bulbous bow below contacting critical bridge piling or foundations, and then the crushing of the bow and any crushing of any sacrificial fender elements. It affects the foundation geometry. What we're looking at in the bottom right here is just an example of a bridge foundation with the support piles and then the columns. This structure does have an overhanging pier protection sacrificial element that is mounted to the pier foundation. And as the vessel collapses, it's actually able to take out the sacrificial piles. But what you want to make sure you consider is that the impact energy that's absorbed by the vessel and crushed by the vessel, we want to make sure that the bow doesn't impact the critical support piles for the foundation. We also want to make sure that there's sufficient overhang where the bow itself, the deck level, doesn't impact with the column. And I've had questions about in previous presentations about, well, does the ship really slice through like this? And the answer is yes. This was a container vessel that actually hit a port facility, and you can see where it actually did crush right through the edge of that deck, actually crushed right through exactly as we're showing it. Some of the things that we can do, some of the finite element modeling of the vessel impact. It is a complex problem. It is a nonlinear dynamic modeling of both the impact and ship grounding. As such, we do use an explicit solver FEM modeling for this. What you're seeing is This is a HandyMax type vessel. This is a FEM model of the HandyMax vessel where we've accounted for all of the ribs and the support structure. In this middle one, what we're looking at is the ability of that vessel to actually ride up on top and what kind of damage is done to the vessel. But can that vessel actually ride up over top of a lower level foundation support? Here we're looking at the grounding of the vessel, how far can it travel, and then up top is once again just a model of the of a vessel running into the pier. So now I'm going to talk about a couple of typical pier protection alternatives. For bridges controlled by ship collision, we're typically looking at dolphin structures. These are large diameter steel sheet pile cellular cofferdams. They're typically a sacrificial element. We're looking at protection islands, and then we're looking at pile supported structures, which once again, they're typically a sacrificial element. For bridges controlled by barge design, we can design piers for impact forces, which means that you don't need anything in addition to what the pier is itself. The impact loads and energies are typically much less for barges than they are for ships. So maybe the pier can be designed to actually handle that. We can design fender systems both elastically and sacrificially, and dolphin structures, once again, as elastic and sacrificial. For the dolphin structures, as mentioned, they're typically large diameter, 40 to 100 foot steel sheet pile cofferdams, heavily reinforced concrete caps, and they're filled with sand or gravel. They're typically sacrificial. The kinetic energy is absorbed by the ship crushing, and then the dolphin partial and or full collapse. We're looking at a couple of examples here, the Dane Point Bridge in Florida, where we've got the dolphins on the approach. And this is the Incheon Bridge in South Korea, where it's surrounded completely by cellular coffer cells. For the dolphin structures, the impact energy is absorbed by either the crushing of the vessel bow, the lifting of the vessel bow, the friction between the vessel and the dolphin, the friction between the vessel and the bay bottom, sliding of the dolphin, rotation of the dolphin, and deformation of the dolphin. Now, this is something for a lot of structural engineers. It's a little difficult to wrap your mind around it. We're typically designing things in either the elastic or the plastic range. The purpose of these dolphins is a sacrificial element. So if they're hit by the design vessel doing the design speed, the intent is for them to be completely demolished. So they would need to be replaced after the incident. But certainly the replacement of a dolphin type structure is much less than the replacement of the bridge. But designing something to collapse and fail for structural engineers is sometimes a foreign concept, and it's hard to wrap our brains around. Ultimately, the structure needs to hold together for about 3 to 4 seconds. And how we do that is typically with put a heavily reinforced concrete cap on top. One of the things I do recommend is that for that concrete cap to be the physical attachment, to make sure that it's not just kind of sitting in and self-weighting in. I have seen examples where the original design had an embedment of the steel sheet piles up into the cap. However, the contractor, it was going to be kind of difficult to build, so the contractor asked if they could just build it inside of, and they did. And then when it was hit by a vessel, this large diameter, very thick concrete cap just basically flipped out onto the sand bottom of the waterway floor there. So we need to design it to make sure it holds together for at least 3 to 4 seconds. That may entail some welding of steel sheet piles together, but ultimately we just need to make sure that it absorbs the energy, it can handle the force, and it holds together for that duration of time. This is an image from the AASHTO guide spec that shows the dolphin after impact. The next to discuss is island protection. Island protection would be considered the best protection when it's environmentally feasible. The problem with this type of measure is that, especially in U.S. waterways, islands typically cover a large area of waterway bottom, and that can become a problem with environmental permitting. So they do operate the best, but the environmental permits to obtain can be certainly a challenge. This is an island protection structure that was put around on the Houston Ship Channel in Texas. Here's an island structure at the Cooper River Bridge in Charleston, South Carolina. And here are some island structures at the Singma Bridge in Hong Kong and China. For the island protection, the impact energy is absorbed by the grounding of the vessel. Once again, you have the lifting of the vessel's center of gravity. You can have crushing of the vessel hull, although it's usually minimized. There is a generation of water waves and turbulence and hydrodynamic mass coefficient. There's displacement, shear, compaction, and crushing of the island material. So it does damage, and there are usually generations of shock waves in the islands that can be transposed onto the pier foundations. The islands do the least amount of damage to the vessel, and as such, they have minimal risk to oil spills. So they can be environmentally on that side of the equation. They can be a little bit more environmentally friendly, and they're usually easily repaired after an impact or grounding. For those that have ever driven down a large highway through the mountains and have seen the runaway truck ramps, I typically liken an island to that type of a philosophy. You're trying to create something that's going to be somewhat of softer impact. You can actually do a combination of different types of structures. You can have dolphin and island combinations. Here's the Sunshine Skyway Bridge in Tampa, Florida, which has both the cellular coffer cells and an island. An interesting story about this bridge is that the day the replacement bridge opened, there was a fishing trawler that actually hit one of these and sank a few minutes later. Turned out that both the captain and his crew were in back tending lines, and they had the vessel on autopilot, but it was hit almost immediately after, small vessel, but it was hit immediately after put in service. The last type is the pile supported type structure. These can be done in two ways. What's shown here on this bridge in Argentina is actually a separate type structure. So it's separated, it's a pile supported structure that's separated from the bridge pier. If the bridge pier is substantial enough and can handle the lateral loads, you could certainly mount it to the bridge pier, although it's less desirable because there's a lot more geometry involved in that, as shown previously, making sure that the deck and the bow do not contact with critical members of the bridge. You'll note that on this bridge, actually there's larger structures on one side versus the other. The reason for that is this is on a river, and the river currents are flowing one direction only. And so vessels are transiting in one direction a lot faster. They're transiting in this direction a lot faster than they are in the opposite direction where they're going against the current. So therefore, the difference in size of the two types of structures. This is a pile supported structure. It's actually right adjacent to the Francis Scott Key. Mike and I worked on the vessel collision risk analysis for this. It's the BG&E 230 kV crossing. So it's a high tension power line crossing. It had a 2,200 foot main span, and it was designed with a sacrificial pile support ring. So this support ring that we see around it was essentially put in place, pile supported. It's there to crush if something were to get awry, crush and protect the foundation structure for the towers themselves. With the 2,200 foot main span, we were able to locate the piers in shallower water depths versus the dredge channel, and a lot of the larger ships we determined through the finite element analysis, would run aground before they were able to make contact. There's also operational measures that can be instilled to reduce the risk of collision. The reminder that the navigation is regulated by federal agencies, both the U.S. Coast Guard for coastal waterways and international commerce, and the U.S. Army Corps of Engineers for inland waterways and domestic commerce. The bridge owners themselves cannot impose navigation of operational requirements in the waterway without the federal approval and input from the maritime users and organizations. So we can certainly look into measures, but there's a process that has to go through to get these measures implemented. The operational measures include bridge-mounted surveillance devices to monitor vessel transits. A lot of this has actually been in use on a lot of bridges in the U.S. A pilot master emergency communications with police and bridge operators to shut down highway and rail traffic. I think we saw that implemented in during the Key Bridge when they were able to radio to the proper authorities and they were able to shut the bridge down to traffic for a situation that could have been much, much worse. You can establish a U.S. Coast Guard restricted navigation area near the bridge. And then you can implement speed, visibility, and water current restrictions for vessel transits. These operational measures, a lot of times what we need to do is verify their impact on the actual maneuverability of the vessel. So we can use this. We use ship simulators to evaluate the vessel operation and the navigation alternatives as part of the whole entire comprehensive bridge protection program. So for instance, if we have a speed restriction, we want to make sure that the speed doesn't make the vessel and the maneuverability of the vessel. We don't make sure it doesn't impede that, because then we've actually created more of a problem than previous. So this is an actual image of a pilot in a simulator piloting a ship, looking to make sure that the restrictions that we've implemented do not cause these issues. The second edition of the Vessel Collision Guide Specification did have some planning guidelines. Some of these guidelines are just rules of thumb, but very good rules of thumb. That bridges with main spans less than 2 to 3 times the design vessel length are particularly vulnerable to vessel collision. So if the vessel length is 1,200 feet, which is fairly standard for some of the larger container ships, then the main span should exceed 2,400 to 3,600 feet. And this is obviously planning for new bridge construction. Same for bridges with main spans less than 2 times the channel width are particularly vulnerable to vessel collision. So if the channel width were 1,000 feet, then the main span should exceed 2,000 feet in this example. Some final thoughts of things that you should know: that bridges are obstructions to marine navigation, that mariners have the right of way, not the motorist, that bridges must provide for the reasonable needs of navigation, that bridges must, sorry, technical error on my part, bridges must provide for the reasonable needs of navigation, that bridges are permitted to be built as obstructions to navigation by the U.S. Coast Guard, and as such, those bridges must be maintained in accordance with U.S. Coast Guard permits. Of particular note that when there typically is a collision, a mass collision incident, that these things are handled in what's called an admiralty court. And in admiralty court, if the bridge or the vessel owner can prove that the bridge was not maintained in accordance with the permits, they can actually sue the bridge owner for failing to do so. And it's happened in the past where the bridge owner is actually responsible for the damage done to the vessel from collapsing a structure. So it can happen. So the other thing to consider is that bridge and vessel collision vulnerability studies in the US, they're typically highly confidential and classified. They do point out weak points in the infrastructure, and as such, and especially with terrorist considerations, that's why some of this information is highly confidential. Some vessel collision resources. As Mike mentioned, that we have the vessel collision, the second edition of the Vessel Collision Design of Highway Bridges. There's also a document done by PIANC. It's an international document. I'm the principal U.S. representative for a re-edit of this document. This one was done in 2001, but we're doing it under Working Group 215 right now. So looking to come out within the next year, the update to this should happen. Another useful resource is called the Green Book. It's the IABSE document. Dates back to 1993, so they're looking at an update to that. Mike Knott and I have both been asked to be a part of that code or that document update. And then there's another one that say it's proceedings of a ship collision analysis symposium that was held back in the early 2000s. One of the things that note here is that should the AASHTO Vessel Collision Guide Specification, should it be updated? And I've stood on a soapbox and said absolutely. The document was updated certainly in 2009, but those were basically transitions to the LRFD code. So it dates back to the original 1991 publication, of which the data that went into that was from the 70s and 80s. There's been a lot of information, new information that's out there. There's a lot of new procedures out there, and it would do well, especially given the nature of this being on the front burner, to look at doing a re-edit of this code. Would be good to do this now. For the folks like the Mike Knotts that are aging, to be able to do this to where we include them in this rewrites so that we can understand and appropriately know the information that went into the development of the original codes. Otherwise, I fear that we may lose some of that. So I stand on, like I said, my soapbox, and I try to. I think we really should do a consideration of updating this vessel collision guide specification, and as such, that would roll into the code as well. And I think that's it. I do appreciate your time today. I love this photo. This is actually in the Vancouver Harbor we looked at. What you're seeing in the foreground is the arch truss for the Ironworkers Memorial Bridge. And then shortly and just immediately adjacent to it is an old railroad bridge that's actually been hit and taken out several times. But this is ultimately, this is the threading the needle with the vessels. And this is from the pilot house. So you see what they're dealing with. So with that, I will end the presentation.
Thank you, Michael and Mike. That was a very interesting presentation on a topic that's been on many of our minds due to recent activities or recent events. We have had a number of questions that came in both before and during the presentation. Paul Lyles, the former Georgia State Bridge engineer, will start the question and answer session. He'll be joined by Don Diggeman, who is the current Georgia State Bridge engineer, further on in the Q&A. Paul?
Okay, thank you, Kathy and Mike. Really interesting presentation. We'll get into the questions. We've got some here. The first one was just, what are the most effective forms of vessel collision mitigation?
Thank you. So if you can do an island around a pier, obviously that's the best. Vessels run aground, but it's not always practical or implementable due to environmental conditions. So for inland waterways with mainly barge collisions, fender type systems I think work well. We have to consider the overhang of the empty barge making contact with the pier column. For new bridges, those columns can be designed for an impact force. For older bridges, I think a fender system that helps that to not happen is the way to go. But it is somewhat site specific. It comes down to the water depths, the soils, and some environmental concerns. But protection islands, dolphin type structures, pile supported structures, those are in the toolbox, and we can adapt them for a particular site situation.
Okay, then the other wrinkle to that is, which one is the most cost effective? You might want to do a hierarchy on those or something.
Sure. Well, these days, dolphins are fairly expensive. A typical 80-foot diameter dolphin in 40 feet of water typically runs around $10 million each. So you put 10 of those around a structure, not just the main piers, but some approach piers, and you're approaching $100 million without blinking an eye. Islands, well, there are no cheap alternatives. I guess I'll say they're all going to cost money, and when you're retrofitting an existing bridge, the cost quickly can exceed replacing the bridge. So one option of pier protection is simply to replace the bridge, and that could be a cheaper alternative than trying to protect it. But funds are not unlimited, and so I think something important in this discussion is cost effectiveness. And that was one of the reasons this method 3 was in the original guide specification, is that you could quickly run out of money, and yet you can ask the question, well, with a limited amount of money, what's the best I can do? And so using these cost effectiveness procedures with the risk analysis can say, if I have so much money to spend, this is the best place to spend it.
Okay. These questions came in before the webinar, but we'll go ahead. Please discuss which entity is responsible for performing the risk analysis related to large vessel collision.
Thanks. Yeah, I'll take this one. So it ties into my comment about design build projects. typically the owner would engage an engineering firm that would do the analysis. But some of the assumptions that go into that analysis are in discussions and consultation with the owner, who has the ultimate decisions to make. So typically the engineering firm doing the bridge design would do the risk analysis.
Okay.
Now for some projects, what's appropriate, and this gets back into design build situations, it's important, I think, that the contractors are on a level playing field. And so the owner can do the risk analysis and provide that information to all the consultants and say, here are the rules, here are the criteria, here are the assumptions you need to make, and make sure that all the firms are competing on the same basis.
Okay. How is the vessel passage data collected? And please discuss some of the sources and how the counts are determined.
Mike, I'll let you take that one.
Yeah, absolutely. This goes back to the AIS data. So what we do is it tracks, let me see if I can page back up. It tracks the vessel transits, and it tells us the vessel speeds. So it's information like this. So like I said, all large commercial vessels are required to have an AIS indicator on them. So it tracks the vessel passage, it tracks the vessel speed, tracks the vessel name, the type, the category. A lot of times it'll track the loading condition of the vessel. So this is the type of information we would use to establish the vessel fleet. You can certainly take this and have conversations with local pilots, with operators in the area, and kind of back this up. But this is how we would typically establish the vessel fleet for a certain waterway.
And just to add to that briefly, so you get a listing of every ship that transited the waterway in a calendar year. So if there was 10,000 trips coming to a port facility, there'll be 10,000 entries in a database that you'll get from the AIS folks. And that can be processed in different ways. We get the names of the vessels, all the specifics about them. Now, AIS is also used in the inland waterway system. So towboats that are pushing barge tows also have AIS, and that information can be downloaded and looked at on inland waterway systems. One of the entries in the AIS data field that the vessel has to provide is its length. And sometimes in inland waterways, the tow operator will put in the length of his towboat, say it's 65 feet. But the length of the tow is maybe 1,000 feet because he's got 5 barges in front of him. And so you may look at the AIS and say, here was a vessel with 65-foot length, but actually it was a 1,000-foot long barge tow. So you need to always take this information and apply some judgment and do some follow-up conversations with the tow operators to make sure you understand what's really happening in the waterway.
Okay.
Back in the day before we had all this fancy automated data, a lot of it was done, Mike and I would sit around a table, we would make phone calls to a lot of the operators. There are some data books, the Waterborne Commerce of the US and the Waterborne Transportation Line of the US. These were all old hard copy books that we would open up and crack open. And as part of the risk analysis, the data collection for the vessels would typically be the most time consuming. It would take us weeks to sit down and actually develop a vessel fleet.
Okay. One of the questions that came in during the presentation is there AIS tracking data available for the Mississippi River barge traffic? And I guess the answer there is yes.
I think so, yes.
Yeah. Okay, that's great. Another question came in beforehand. Ships become harder to navigate as the depth below the keel becomes shallower. Should channels be dredged deeper for larger ships?
So that's a good question. So the depths of channels are regulated by the federal government, and obviously dredging is a huge environmental issue, and so there's pressure to not dredge more than absolutely necessary. Underkeel clearances is a key component of navigation channel design, and so that is looked at because the question is correct, it does affect the maneuverability of the vessel. So that is something that's considered in navigation design by the Corps of Engineers and the consultants that do that type of work. And where there's pressure to deepen the channel, sometimes that can happen, but it would be rare, I think, in the U.S. to see a coastal channel greater than 55 feet, unless there's some natural water depths to dredge below 55 feet. It's probably a difficult proposition. And It takes years and years to get funding for dredging projects. It's a long, slow process. But for vessel collision, it is a factor. So one of the factors that goes into the risk analysis is a hydrodynamic coefficient for the vessel. And that coefficient is based upon the under-keel clearance between the vessel and the waterway it's moving through.
Okay, I want to pick a couple of them here on slide number 11, if you can go to that. On the slide number 11, who determines the probability of aberrancy, and really how is it determined?
So the PSAB has some sub-equations to it. One of them is what we call the base rate, and there's a base rate for ships and a different one for barges, which represents from historical accidents and collisions the rate at which a vessel is in trouble for whatever reason, human error, mechanical failure, whatever, are all combined into this base rate. And then that rate in the code can be increased. So if your bridge is near a turn, depending upon how steep that turn is, you apply a factor that increases the rate. If your bridge is located in an area of high currents, particularly cross currents, that would push the vessel sideways. Depending upon the value of those currents, the rate also goes up. If you're in a waterway where there's a lot of transits, and so vessels are routinely passing and overtaking each other, particularly in the vicinity of a bridge, there are yet more factors to increase the rate. Now, what the code doesn't include is things that can decrease the rate. And that's where, since the code was written, we have portable navigation devices like GPS that pilots carry on board in their pocket. There's some waterways have certain navigation restrictions that, so these things can be looked into to reduce the rate and should be, but it comes down to, again, some engineering judgment, and these decisions need to be made in consultation with the owner. Now, I have seen people try to take the probability of aberrancy and break it into many, many subcomponents. You can build an elaborate fault tree with hundreds of contributing little decisions and put probabilities on all these things that could go wrong and build up in a very sophisticated way a probability of aberrancy. In my opinion, I'm not sure when you do that, you get an answer that's more accurate than a rather crude empirical way of determining PSAB, which is what the code does, because you have to make assumptions about all these subcomponents, and frankly, the research isn't there for most of them to say what they are. So at the end of the day, having a base rate based on real accident data, which the code did, I think is an appropriate way to do it.
Okay, we're about running out of time. I'm going to go ahead and turn it over to Don to try and get one question or so. Don?
Thanks, Paul. Got some interesting questions here. Let's start off here. Is it a good idea to put a lot of faith in our ability to predict the paths the vessel is likely to follow, or to assume that 360-degree protection is more appropriate?
So it's not always 360 protection that's appropriate. So that's like if you put a single dolphin in front of a bridge pier, there's a certain level of protection that provides, and that may be enough to meet the acceptance criteria for bridge collapse. So you don't need to always go completely around a pier. Just protect from the most likely paths that an aberrant ship would make.
All right. I think this was mentioned in the presentation, but question here is, are there any plans to further develop provisions surrounding superstructure risk, like deck furniture or crane barge strikes?
That if there's an update to the guide spec, I think that's something that could be added to it. There is some information about deck house impacts in the AASHTO code, but I think that's an area that we do have some more information on, and that could be an area that's updated. But for arch type bridges, which there are some, of course, in our country and overseas, sometimes a simple mast collision can take out a bridge. And so understanding what those forces are and the ability of the bridge to resist those forces is something that can be done, and is something that has been done. We have done that on some waterways to make that analysis and to make some recommendations to protect it.
All right, just to break up the questions here, there's a statement more than a question. Thank you from New York. So going next to the next question, have there been cases where piers or vents have been improved or retrofitted, such as using CFRP wraps to help increase structural capacity for vessel impacts? Could this become a more feasible option in the future?
I think everything should be evaluated. Certainly could be something. I think one of the takeaways from what Mike and I want to say today is it's also energy in addition to force. And so being able to dissipate energy, and FRP type structures certainly have a role to play and should be considered in certain applications.
Okay. Take on a couple more questions. Is vessel age considered in the risk analysis?
Not really. The age of the vessel is not, but we do try to look into the future, 50 years ahead to the midlife of a bridge if it's a 100-year lifetime, to make a projection on what vessels might be. Now this is a crystal ball for sure, and is an area of judgment and discussions with the owner. But we should be thinking about certainly more bridges, more ship transits in the future by bigger ships. But there is a size that ships can't go beyond for most waterways, particularly in the U.S. Ships with depths that exceed 52 feet are probably the limit on U.S. waterways. We have bridges where there's vertical clearance limitations where vessels can only get to a certain size. And so there are places around the world where the ships are extremely big. They could never, with 60-foot drafts, they could never enter a U.S. harbor. So there are some limitations in the U.S. about how big vessels can get. But on coastal areas where ships don't have to go under a bridge or through a bridge and the water is deep, particularly like in the Pacific Asia trade, the ship sizes can be enormous. But thankfully, we don't have to worry about those in the U.S.
Don, we're getting a little long on time. Obviously, this is a topic that everybody is really interested in. Great questions, but I do want to be a little respectful of the time. So we do want to thank Michael Knott and Michael Winters. Thank you very much for sharing your time and expertise. It was obviously a very interesting presentation. A thank you to Paul Lyles and Don Diggeman for helping us with the Q&A. Quick reminders on both the engineering conference. Please get registered right away. Early registration ends August 23rd. And please do register also for the in-depth web training on September 10th. That will be all. We thank everyone for joining us today, and the webinar is now concluded.